So far, all of the ions that we've talked about consist of a single atom with a charge on it. But there are a lot of ions that are very common that contain more than one atom. For example, if I take a carbon atom, hook it to a nitrogen atom, and put a negative charge on it, that is a very stable ion that is called a cyanide ion. And you can, once you know the formula and the charge, you can build ionic compounds from this polyatomic ion the same way we were doing in the last video with elemental ions. For example, suppose I want to write down the formula for aluminum cyanide. I'm going to follow the same steps we did in the last video. I am going to write down the formulas for each of those ions, and then I am going to put the ions together so that they electrically neutralize each other. So I need the charge on an aluminum. I look at my periodic table, see where aluminum is. It's in the column with +3 ions. So I can write aluminum +3. Cyanide I cannot look up on the periodic table. Where do I get that from? You're going to have to memorize that. You need to memorize the formula and the charge. Now I need to put these two things together so that they electrically neutralize each other. Now, how many cyanides with a -1 do you think I'm going to need to put together with the aluminum? 1 is not going to be enough, right? I mean, if you put just 1 there, you'd have a total +2 charge. If I put 2, I'd have a total +1 charge. So I really need to put 3. Now the total charge on these 3 is -3, and that will balance off the total positive charge over here. So my formula is going to be, when I put all those things together, now notice I've done something a little different here. I have parentheses around the cyanide formula. You're going to use parentheses around polyatomic ions. Not always, but when there's more than one. So if there's only one, you don't need to put the parentheses around the polyatomic ion formula, but when you have more than one, you're going to use the parentheses. For example, if I ask you to give me the formula for potassium cyanide, the process would be, let's look up what a potassium ion's charge is going to be. I find it on the periodic table. It's right there. It's in the +1 column. And then I know what the cyanide ion is. I can put those together just the way they are. And I don't have to put parentheses around the CN. So it's not necessary. And notice when I push them together, I take away the charges. I am not going to write something like this, even though I understand why you would want to. Because once they're together, once you make a compound out of those, the charges neutralize each other. So that would be the wrong way to write it down. Once you push them together and make a compound, that would be potassium cyanide. So now you can go both ways too. If I give you the formula for a cyanide, you can write down the name for it. Now let's look at all of the polyatomic ions that are common that you should know. You will find all of them on the compound nomenclature tips sheet. If you take a look at the bottom of page 1 and page 2, all of the ions that are listed on that page are worth remembering, are worth memorizing. Let's go through them. And it helps as we're going through to group them somehow. It's easier for you to remember a group of objects than it is a random list of objects. So let's group the polyatomic ions as we go along. There are very few positive polyatomic ions. They're pretty rare. This is a big one. This is the ammonium ion. Now, not to be confused with ammonia. Ammonia is NH3. If you take NH3, which we'll see later is called a base because it is something that grabs onto hydrogen ions, it will react with it and produce the ammonium ion. This NH3 is what you know as ammonia. And this is ammonium. So it seems like a small difference in their names, but it's really a big difference in behavior. So let's play with this new one just the same way we did before. What if I ask you to give me the formula for ammonium sulfide? Okay, well, I've got to write down the first step in writing the formula down is to write down the formulas for the separate ions. I need the ammonium ion, which I know now, and I need the sulfide ion. I got to look at a periodic table for that. Here's sulfur. It's in the -2 column. Got it. Now, how many ammonium ions am I going to need for every sulfide ion? If you said 2, that's correct. You're going to need 2 of these things, because now the total positive charge over here is equal to the total negative charge over there. So the formula is going to be this. I pushed the ions together so I didn't have to write the charges in anymore. And I put parentheses around the NH4 because there's more than one ammonium in here. All right, so what other positive ones should I know? This is a weird one. This is 2 mercuries that are hooked together that have a total +2 charge. And what they call it is a mercury 1 ion. Now, why would they call it that? Because you don't see any 1s anywhere in the formula here. Well, picture this ion as looking like this. Now, when I write it down that way, you can see that you have 2 mercury 1 ions. Mercury 1 ions always come in pairs that are hooked together, and we write it down as Hg2 +2. So that's kind of a strange one. Let's play with it. Let's suppose I ask you to give me the formula for mercury 1 chloride. All right, the first thing I'm going to do is write down the formulas for the ions. Now I have to know that mercury 1 is this. You might make yourself some flashcards at first when you're just starting to learn these. And the chloride from the periodic table is Cl-. So when I put these together, how many chlorides am I going to need? If you said 2, you're correct. Then you'd have a -2 if you had 2 of these. So my formula is going to look like this. Now notice I did not need to use parentheses around this polyatomic ion because there's only one mercury 1 ion in there. They consider the pair a mercury 1 ion. So when I say mercury 1, I mean this. So that's a mercury 1 ion embedded in there. I took off the +2 charge because I put 2 -1 chlorides on it. That would be the formula for mercury 1 chloride. What would mercury 2 chloride look like? It will look like mercury 2. The Roman numeral just gives you the charge on a transition metal or a rare earth or anything that is in the main group. We saw that in the previous video where we were looking at reading ion charges off of the periodic table. If I look at chloride on the periodic table, it's got a -1 charge. So when I put it together, I'm going to get 2 chlorides for every one of these. So this is mercury 2 chloride. It has 1 mercury. And this is mercury 1 chloride. It has 2 mercuries. And that shouldn't confuse you because you should be naming this thing from the ions that are inside of it, not looking at the finished formula. There is a third positive polyatomic ion to know, and that is this is called the hydronium ion. Notice that a lot of times these non-metal positive ions have a NiUm ending on them. And these are the only ones that we're going to look at in this course, but there are some others. And you will sometimes see people write the hydronium ion down when they're talking about acid-base reactions. You should know the formula for it and the name. We are going to come back to this later. We're not going to really form compounds from this right now. So I put a box around that. Remember, that's my code for saying that this is something you should know for the exam. All right. What other kind of ions can we look at? If you've got that compound nomenclature tip sheet that's up on the website and you print it out, that gives you everything you know, the complete list. If you look at polyatomic ions that have IDE endings, there are 3 of those there too. One we've already talked about, the cyanide. Another one is peroxide. And it looks like an oxide, but it's got an extra oxygen. You will see this per prefix means add an oxygen. So if you've got oxide is O-2, if you put a per in front of the oxide and get peroxide, that means stuff an extra oxygen into the formula. So we have O2 -2 instead of just O-2. Another one you've already met. There are only 3 of these. It's the hydroxide ion. And we've done a couple of experiments with this already. We looked at it in our ion conductivity lab, remember? So there's 3 of these too. It always helps me when I'm memorizing lists to know how many are in the list. So I know there's 3 polyatomic ions. If I can remember 2 of them, I can think, oh, there's a third one, and I won't miss it. Same thing with the IDE ending ions. There's 3 in the list that you should know. And we can build compounds out of these. For example, this compound is used to convert river water into drinking water. They will form some aluminum hydroxide in the river water, and it is sticky and gooey, and as it settles down to the bottom, it will grab onto bacteria, viruses, dust particles, mud, whatever, and hold on to it. And it'll settle down into the bottom of the tank. Then they can skim the water off the top, and the water doesn't have all of those things in it then. Let's write down the formula for aluminum hydroxide. If we look at aluminum on the periodic table, which we've done a couple times now, and we know what hydroxide is, then I can put these things together and I can make aluminum hydroxide. I needed 3 of these for every one, and I put parentheses around the hydroxide in order to get the charges to balance. Okay, this is running a little bit long, so I'm going to have to start another video to do the rest of the polyatomic ions.